Okay, for one block diagram, we're looking at what order this is. It's in parallel. Add, multiply the u of s, figure out what the highest exponent of s is, common denominator ends up being 2, so a second order. And now we're trying to figure out what the gain of g of s is. Rearrange that. Gain constant ends up being k of 1. Now we're trying to figure out what the poles of g of s are. Poles come from the denominator. Set it equal to 0. Figure what s needs to be to make that true. Ends up being 0 and negative 1 over tau. Little graphy. What are the zeros of g of s? Zeros come from the numerator. Z of 1 equals negative 1 all over tau plus k2 over k1. You have one finite zero unless k1 tau plus k2 equals 0. And if k1 all over k1 tau plus k2 is less than 0, the 0 is in the right half plane. Therefore, you have two options. K1 is less than 0 and k1 tau plus k2 is greater than 0, or k1 is greater than 0 and k1 tau plus k2 is less than 0. And then from there, what conditions will the process exhibit both a negative gain and a right half plane is 0? Gain equals k1. You end up having to pick k1 is less than 0 and k1 tau plus k2 is greater than 0. And then for F, for any input change, what changes of time, the response nodes will be included in the response. This also comes from the poles. Inverse Laplace, you have a constant and E equals negative t over tau. G is the output bounded for any bounded input change. For example, U of t equals m, y of 1t equals k1 mt. That's it being a ramp function. And this grows that limit. That's just how ramp functions work. But if the input is m over s, the output will contain an s term. A t term that is not bounded since it's a ramp input. Going down to the one that I understood the least, we have 5. I had problems with the overshoot, but I think I understand what's going on now. Of u of s, this is our block diagram. G of s equals y over s. U of s, it's in series, multiply them. Figure out what a zeta is. Zeta is, if it's between 0 and 1, that's a big overshoot. It is overshoot because zeta is 0.5, and then we also need to compare tau 1 and tau 2. Tau 1 is 0.1 and tau 2 is 2. Since tau 1 is so much less than tau 2, we can assume that tau 1 is relatively instantaneous compared to tau 2. Therefore, the first element can approximate to e equals negative 0.25s. Simplify that here. B, what's the approximate max value of 4 for k equals k1, k2 equals 1, a step change of u of s equals 3 over s. We're looking at overshoot with zeta being 0.5. That ends up being 0.163. And for a 3-unit step change for y of max, we have 3 multiplied by 1 plus the 0.163, and ends up being approximately 3.5. Now we're trying to figure out where the maximum value occurs. Plug all those variables into this equation using 7.3. And now we're looking at these graphs. We have for tau 1 equals 0.1, you have faster poles. The system behaves more like a clean second order system, and the SOPD approximation works a lot better. Both models are approximately the same. And those SOPD model gets worse as tau 1 increases, since the first order and time delay are not the same thing. This one is tau 1 equals 0. The poles move closer to a dominant pair. Response is slow, and there's less overshoot. And for tau 1 equals 5, you have real poles at negative 0.2. You're now competing with complex poles, and the system is much slower. Yay.